Hey, I'm Luke with S&S Diesel Motorsport. We've had the Ford CP4 to DCR conversion out for about a month and a half now. It's towards the end of July 23. We've got 2,200 or so of them out there in customer hands in a pretty short period of time. Customers have been super excited, great reception, and it's been a great product. And we want to address some questions we get. There's more people who want to learn more about it as people are hearing about it, and want to dispel any myths and answer any questions about how the pump performs, output, sizing, things like that. So the pump displacement in this case is 1,250 millimeters cubed per rev. I'll show here in a little bit how that's calculated. But one thing we want to clear up too is there's been some people bring to us that there's some rumors of how our pump sizing is versus how it actually performs being inaccurate or dishonest. And integrity is incredibly important to us and our reputation here. And while what we have and what we've communicated is factual, I think there's misinterpretations with folks that may not understand how things work. So we'll show how that works. We'll show some comparisons on flow data versus RPM versus other CP4 variants, and get into some graphs here in a second. So this is a cutaway of the DCR. We have always advertised it as 1,250 millimeters cubed per revolution. So that's millimeters cubed is a volume measurement, like liters, like gallons, like any of that. And that is basically how much displacement per revolution that pump has, similar to how engines are sized. And this is the simplest way to size pumps. That's the way that Bosch sizes pumps. That's the way most OEs or people that really understand how the fuel systems work size it, because the actual flow of the pump is highly dependent on other things like supply pressure, like RPM, like IMV or FCA, milliamps, and rail pressure as well. So there's lots and lots of factors that affect the actual flow of the pump. But the one thing that is fixed is the actual dimensional displacement of the pump. Just like how an engine is a 6.7 liter Power Stroke or a 5.9 liter Cummins, that is the dimensional displacement of that pump, and that's the easiest way to spec it. Bosch does it the same way with the CP4s as well as CP3s, and I'll show and explain that here in just a second. Here's a simple little table I put together that shows how the sizes of the different versions of pump are calculated. So sometimes you may hear R90, R99, that type of thing. That is a little bit more of an internal name, but that actually is on the side of a CP4 or a CP3, has different values as well. The R basically means right-hand rotation. There are left-hand rotation for like rear gear train engines, that is a reverse rotation pump. But the R is just rotation of the pump, and then for Bosch anyways, the 90 or 99 or 80 refers to a displacement just like the DCR is spec'd. That's millimeters cubed per rev, rounded, and then with 1 0 missing. So without getting too complicated, an R90, like an LML Duramax, 11 to 16 Duramax, and an 11 to 14 Ford use an R90 sized pump. That's 90 referring to 900 millimeters cubed per revolution. In 15, they went to a little bit bigger pump. Some people refer to it as a CP4.2. They're all CP4.2s. A 0.1 is a one-cylinder pump like in a Volkswagen or a little engine. All Fords are CP4.2s, but in 15, they just changed the stroke to go to a slightly longer stroke. That is called an R99. That 99 basically refers to 995 millimeters cubed per stroke. So you can see here, 6.5 millimeter bore on all these, 6.75 stroke for the R90s. It goes to a 7.5 longer stroke. In the most basic terms, this is just a super simple example here. This is a 4-H project from when I was a little kid that my dad and I built. This is just a Briggs engine, tore apart, but I saw it this morning when I was thinking about explaining how these pumps work. And an engine is just an air pump, just like a DCR or CP4, it's just a fuel pump. They have a bore and a stroke, and they move air or fluid based on that. So we're talking literally the bore diameter of the cylinder, and then the stroke being the distance that the piston travels up and down. So that's what's input into here. In the case of a CP4, it's a 2-cylinder pump, and actually there's 2 strokes of each plunger or piston per revolution. That's how they can get away with a really small, compact, lightweight pump and still get enough output to make the 400, 500 horsepower that the factory truck has, is because they actually have a 2-lobe cam that makes those plungers go up and down twice every revolution. So that's a difference here, but these are all factors that go into that calculation. So without getting into too many details, this is basically a comparison. R90s from the earlier generation CP4s, R99, that's the displacement of that pump. The 6.7 Cummins, the 2019 to 2020 Cummins, is actually an R80, which you might think, well, that's odd because that was 1,000 foot-pounds of torque, factory rated engine. It's got a ton of power, needs a lot of fuel. Well, difference here, see, it's actually a short stroke, 6mm stroke, but the difference here is that pump is driven at 1.5 to 1 engine speed. Everything else drives at 1 to 1. Whatever engine RPM is, that's what the pump RPM is. In this case, it's 1.5 to 1, so it's overdriven quite a bit. So it actually went to a short stroke, but they can get higher flow out of it by spinning it faster. Something interesting, we actually had a 2023 in here the other day and checked that pump out, and on the side of that pump, on the tag, it says R113. So I don't know exactly, I've not had it apart, I don't know exactly the dimensions of the bore and the stroke, but Bosch tends to stick with a common bore usually that they have, that they're comfortable with. But in this case, you can basically just kind of play with the numbers and see what you think it might be. So an R113 would mean add a 0 to it. It's somewhere near 1,130 millimeters cubed. Well, if you stick with a 6.5 millimeter bore, it takes an 8.5 millimeter stroke to get there. And see if you change that to 8, then we're gonna be too much. But so it'd be interesting to see, they went with a fairly high displacement on the 23s. It'd be interesting to see whether that's all stroke. That's a pretty long stroke for a factory pump that they're expecting to live very long. So we'll see what happens. Anyways, compared to a DCR, biggest difference is the bore in the DCR is quite a bit bigger. So here is the DCR, it's a 9.5 millimeter bore, 8.8 millimeter stroke. That equates to 1247 rounds to 1250 basically. So this is what the displacement is versus an R90, earlier 11 to 14 pump, and an R99, 15 and up, 6.7 Ford. This is a comparison to a aftermarket 10% CP4, which is an 8.25 stroke, or a 10.3 38% aftermarket pump is a 6.5. If it's got a 10.3 stroke, then that's 1367 millimeters cubed per rev, which is actually 37% over, not 38, but math is hard sometimes, so I get it. So anyways, this is how that's calculated. And like for example, a little 2-liter CP 4.1, it's got a little 5.25 stroke. So these pumps are basically like engines. If you think about it that way, it helps to really kind of simplify things. The difference is you take that displacement just versus RPM. In a perfect world, that would be what the flow rate is. But the volumetric efficiency, these things changes versus RPM, supply pressure, all those things that I was mentioning. We've collected a lot of data already. We've done a lot of validation for the last, couple years on this thing. The hardest part is making it be a drop-in replacement into the Ford. So to be clear, the DCR has always been designed to be a factory drop-in into a stock truck that anybody can just put it in just like a replacement pump, not have to do any tuning. It's emissions compliant. It is a reliability, robustness drop-in. That's what everybody wants, is a reliable pump so that they can go use their truck and not have to worry about it. So it's been heavily focused on that the whole time. With that being said, that pump is higher displacement than the factory CP4s, like you can see here, I skipped this a little bit, but the DCR is actually, it's a little over 25% more displacement than an R99, which is a 2015 and up, the bigger CP4 in the Ford. But we just round down to 25. If you compare it to an earlier gen, 11 to 14 Ford, it's actually 39% more displacement. With that being said, it's been developed and designed to be able to follow the factory curve so that the truck and the ECM and the rail pressure control doesn't know any different. This base DCR pump has been out there for a long time. It's not a brand new pump. It's been out there used in bigger engines for quite a while. We worked with Standardine and Pure Power to take a base bore stroke pump body architecture with different cam, different other internals, and all kinds of different parts to make it work into the Ford application. So the base pump is not a new pump. It's a well-validated pump. There's hundreds of thousands of them out there. But it is bigger displacement because it actually originated on larger engines. We're actually adapting it to a smaller engine that it normally lives on. So a normal application truck, this is flow, liters per hour, and this is milliamps of current commanded to the IMV or FCA or VCV, whatever you want to call it, on the inlet of the pump. So that throttles flow into the pump, which equates to flow out of the pump. The higher the current, the more closed that thing gets. So if you unplug it, that's why if you unplug a pump, it actually goes wide open, because that basically runs way over here to this end of the curve. This is an R90 versus an R99 versus the DCR. So this thing's been intentionally developed to follow this curve. You can see it just beautifully follows the curve here. A normal common rail pump usually operates between 400 milliamps, which is effectively wide open, and 1700 milliamps, which is full closed. A normal application of the Ford doesn't usually ever get past 1,000. This is all extra headroom. And they do that on purpose because they know that there's likely going to be leakage in the system at times. They got it designed for end of life where the injectors have a lot more wear, the pump has more wear, there's extra leakage, so there's always extra headroom on the top end. Normal application operates down here. So if you're, the normal everyday guy, you're a hot shot driver, your truck's running here, and DCR is just going to follow up and down this curve, do exactly like what it's supposed to. Some guys want to know what is max output of the pump. In the case of Ryan Reiser's race truck, for example, 670 truck running ODSS circuit, and it's got a DCR on it. It's going to have Motec full controls, and it's going to need to make a lot of power for the drag strip. You want more output. So this now is a graph of 400 milliamps, so that's effectively wide open, versus RPM. So this is just what this pump can do versus RPM. This is at 500 bar. DCR is up here. This is an R99, so the later model pump. And then this is the percent difference between the two. So in this case, displacement of the pump is 25% larger. So it actually lines right up here. This is relatively low rail pressure. But you can see the CP4 actually has some efficiency issues out here, and we've shown this with our disaster prevention kit stuff as well. Our disaster prevention kit actually helps to dampen out some of these pressure waves and flow variation that happen in the CP4. But the DCR is a pretty straight, nice, smooth line, but the percent difference varies because the CP4 actually falls off up here at higher RPM quite a bit. So this is the main comparison there. If you do this at high pressure now, so this is 2,000 bar, this is max pressure that any 11 or 19 truck will see. So we've mapped out, we've done hundreds and hundreds of data points on varieties of pumps and different test plans because we've got the capability with our testing equipment, and we fully validate and map things out here. You can see this shifts a little bit because at high pressure, you have more plunger leakage. So just like on this little guy here, rail pressure is going to be on top of the piston. So the higher the pressure, you're always going to have a little bit of blow by or a little bit of plunger leakage. On the DCR, it's a pretty big bore, so you've got a lot more circumference of area to leak. And on the CP4, it's a really small bore, but it has a lot more strokes per rev and a longer stroke in general. So with the bigger bore of the DCR at low speed and high pressure, there's more time for the high pressure to leak past with a little bit of plunger leakage there. There's always going to be some amount of plunger leakage in that system. We're talking, you know, almost 30,000 PSI. So there's always going to be a little bit past there. But if you cherry pick a data point, for example, if you take a bigger bore pump like the DCR and you run it at really low speed, like 1,000 RPM, but really high pressure, 2,000 bar, the truck will never run there. It'll never operate there. But if you want to try to cherry pick points and make the DCR look bad, you'd run low RPM, high pressure, and then say that it doesn't flow very much. The reality is that the truck normally operates more like in this range of RPM, and this is the 2,000 bar versus R99 full flow. There again, the truck rarely ever would operate here, only if it was in a race truck like Ryan's, or it was some max effort situation, or if you had a lot of leakage in the system, would the pump ever have to get this open? But you can see at higher pressure, there is more leakage in both cases, so both curves actually shift down some. And at lower RPM, the DCR is slightly lower because of the bigger bore and the bigger leakage. But once you get up here at higher RPM, it actually does quite better. So even though it's only 25% more displacement, it's actually 40% almost more output at high RPM. So for a competition guy, this is perfect because it actually does pretty well up here, where the CP4 is actually does a wave and falls over. So another comparison versus the R90, this is if a guy had an 11 to 14 truck. There's actually as you'd expect, a bigger jump yet in the difference between the two. The CP4 again, like has a pressure wave and falls off up here at 3,000 to 3,500. DCR is a lot more stable. And then the purple is the percent difference between them. Again, this is if the pump is wide open, which almost never happens, but what it really comes down to is volumetric efficiency. This is goes for engines as well, at different RPM and different boost levels. The engine breathing and volumetric efficiency is different. Fuel pumps the same way. Volumetric efficiency is just the displacement of the cylinder times RPM. That's theoretically how much fuel or air something could move. And 100% would be that it's exactly that. So this is volumetric efficiency at 500 bar. So again, this is more like idle type pressures. You can see this is DCR, R90 and R99. They're all really close to 100% efficient up until about 2,500 RPM. So there's different things that affect efficiency. One is pressure, another is RPM, and there's a few other factors, but pressure and RPM are the biggest ones. You can see up here, it starts to become an RPM issue is why they start to fall off on their efficiency of how they're breathing functionally. So the DCR actually does better than both the other CP4s as far as being efficient, volumetrically efficient. You do the same thing at 2,000 bar. So now you've got more of that leakage, plunger leakage, which is normal. And it's a function of the bore of the cylinder. This is the DCR versus an R90, early gen, R99, 15 and up, and then versus a 10.3 aftermarket stroker CP4, which is intentionally built to be like a high output pump, not a reliability pump. You can see low RPM, high pressure. Some of the CP4s are up there. They're not 100, nothing's up near 100 anymore, but they're pretty good. And then you start to hit 2,500 or so, and the efficiency really starts to fall off quite a bit. For all pumps, that's pretty common. But there again, you can actually see the DCR really holds a better line than all the rest of them as far as efficiency goes. It's a little less efficient at low RPM, high pressure, but that makes sense because of the bore. But up at higher RPM, when there's not so much time, because the stroke happens faster, there's not so much time for the leakage, then it really shines. So this is kind of the summary of just flow versus RPM of the different variants of pumps. Again, this is full flow output. Really, where what you really care about is this curve, which is that it matches the factory calibration, and then it's going to work like it's supposed to in the truck. But for guys with egos or competition guys, this is what they want to see. And this is max flow of that thing. So DCR, R90, R99, and the 10.3 output liters an hour versus RPM. So obviously the R90 is the lowest displacement pump. It's going to be the lowest flow, R99. Here's the DCR, and then there's that 10.3 that is more displacement. But so if you cherry pick a point down here and run them, you're going to get one answer. You scratch that down on a piece of paper and post it. But if you actually do a lot of data mapping and real analysis, you'll see the DCR actually outperforms a 10 mil stroker pump up here at high RPM. 3,500 to 4,000, because there's efficiency and pressure pulsation waves happening. The DCR is just a lot more consistent flow up there, and will actually outperform it because of efficiency problems on the other pumps. But that's, like I say, basically just an added benefit of the product that's been developed. It started out as a higher displacement pump. That gives you more room to grow. Any OE, when they do pump sizing versus injector versus power level, you got to start with how much power do we think we need to make for this power level. Every year that gets more and more and more as every truck gets more powerful. And then you got to decide how much leakage we think we're having in the system, and then figure out what size pump has to deliver all that fuel plus some amount of margin. So the beauty of the DCR is it is the only one of any of these that's actually a reliability improvement in a much more robust design. But in the cases where you need it, or you want to extend the life of your injectors, or if you have a PCV that's leaking and it can keep up with more of that, then the DCR is much more capable of keeping up with that kind of flow. So hopefully that helps explain a little bit how the pumps work, how they're sized, displacement versus output, and a little bit of the background on the things that affect volumetric efficiency and flow of the pumps. So if you've got any other questions, feel free to drop them in the comments or ask us info@ssdiesel.com, and we're happy to continue to explain how these systems work, how your trucks work, how our products work, and really try to continue to develop superior solutions in the market to make your trucks more profitable and more reliable. So thanks for the support. Get with an S&S dealer and get one coming your way. Thank you.